Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is material property charts and concept of material indices. In the last lecture, we discussed the following topics. We discussed about the various classes of bulk materials like metals, ceramics, polymers, elastomers, glasses and hybrid materials and their properties, and we also had a brief introduction about the material property charts and the position of the hybrid materials. In this lecture, we will go into much more detail on the material property charts and specifically three material property charts: modulus versus density, strength versus density and specific modulus versus specific strength will be discussed. Special emphasis will be put on hybrid materials like cellular materials and composite materials. And then we will give a brief introduction to the concept of material indices, their definition, and a case study will be discussed. The main keywords for this lecture are modulus versus density plot, strength versus density plot, specific modulus versus specific strength plot, material indices and case study. In the last lecture, we already started with this material property chart of Young's modulus over density. In this plot, as you can see, Young's modulus is plotted along the y axis and density is plotted along the x axis. And as we discussed in the last class, there are some salient features of this plot or this kind of plots to be more general. First thing is that in this kind of plots, typically the both axes x axis and y axis are in logarithmic scale. This actually allows plotting all materials that are known to us in one particular plot. As you can see in this particular plot, that the density of the materials vary over a wide range. Typically, density from the foams start from a very low value of around 10 kilogram per meter cube, and even the heaviest of metals like tungsten alloys or something like that, they actually cover a much higher density of more than 20,000 kilogram per meter cube. In terms of Young's modulus also, we have a very wide range starting from almost 10 to the power minus 4 gigapascal to more than 1000 gigapascal. The density actually depends upon the two main factors. One is the atomic packing density and the other one is the atomic weight of the elements concerned. As a result of that, metals actually have the highest density because metals have high packing factor and metals also have high atomic weight. As far as the Young's modulus is concerned, as we discussed in the last class, the most important factor is the bond strength. And as we know that covalent bond and ionic bond are the strongest ones, and because ceramics have the highest, ceramics possess covalent and ionic bonds. So, ceramics, as you can see in the plot, ceramics are at the topmost portion, that is ceramics have the highest Young's modulus. Among ceramics, diamond with covalent bond and the small atomic size have the highest modulus of more than 1 terapascal. After ceramics, we have the metals, because metals possess, as we discussed in the last lecture, metallic bond, and as metallic bond is weaker than both covalent bond and ionic bond, so metals are less stiff than ceramics. After that, we have the polymers. In case of polymers, we have both covalent bond and weak van der Waals bond. Although covalent bond is strong, because of the interchain weak van der Waals bond, polymers also have very low Young's modulus, as you can see in this particular plot. That leaves us with the two other classes. One is the foams or the cellular solids and the other one is the composite materials. In this plot, the purple plot or the purple balloon near the balloon of ceramics and metals correspond to the composites, while the light green balloon at the lower leftmost corner is one for the foams, and we have also one balloon for the natural materials. Now, as you can see in this particular plot, foams have very low density. This is because of the fact that foams possess almost a very large amount of air in them, and because of the presence of air, foams possess the low density. In case of composites, the density of composites vary over a wide range. This is because, as you can see, the density of composites typically follows this rule of mixture. Actually, density of all hybrid materials follow this rule of mixture, where if rho h is the density of the hybrid material, and if you have n components, like for example, in a composite material of two materials you have two components. For example, it is a metal matrix composite of aluminum and aluminum oxide, or a ceramic matrix composite of zirconium diboride and silicon carbide. In those cases, we have two materials, so I will be 2, and then if we assume that there is no residual porosity, then the simple rule of mixture, that means you simply multiply the density of one particular component with the volume fraction of that component, and if you do the summation of over all the components, you achieve the density of the hybrid material. So, this expression also explains why the cellular solids possess very low density, because one of the phases for the cellular solids is air, and in fact, in cellular solids the air is the bulk phase, because there are many cellular solids with more than 80 to 90% of air in the material. You will come across those cellular materials in the latter part of this course. But what is more important that I want to emphasize here is that because of this relation, the density of composites vary over a wide range, because as you know, composites can be between metal and ceramic, they can be between they can be between ceramic and ceramic, and they can also be between ceramic and polymer. So, definitely if the matrix of the metal has a high density, then the composite will also have a higher density than, for example, a ceramic reinforced polymer, and that is the reason that the density of ceramics vary over a wide range. In terms of the Young's modulus, now Young's modulus of cellular solids, they depend upon several factors. They not only depend upon the amount of porosity, they also depend upon the morphology and the shapes of the pores, and also the orientation of the pores. Now, amount of porosity is the major factor. So, as you have seen from the previous graph already, if we go back to the plot once again, as you can see, the Young's modulus of the cellular solids like foams are very low or rather low, and this is because of the fact that again the bulk phase in these cellular solids are air, and because of that, this filling of air, the cellular solids also possess a low density. But as I just mentioned, the density of cellular solids is not only a function of the amount of porosity, it also depends upon the pore morphology and the orientation of the pores. Again, these things will be discussed in much more detail in the future lectures. But to give you a brief introduction, I refer to the next slide, where I briefly discuss about the influence of the pore morphology. So, as you can see in this particular plot, so this plot actually shows the two different cases. The left hand side is the case of a spherical pore, that means it is a pore with an aspect ratio of 1, and these materials, because the aspect ratio is 1, so these materials are typically isotropic. That means isotropic means that the modulus is the same, or the Young's modulus is the same along all directions. However, very often we come across situation where the pores are not exactly spherical as is shown on the left hand side, rather the pores are ellipsoidal, That means they might be flattened, they might be elongated and so on. In this particular scenario, the pores are flattened along the z axis. So, what you get in this particular case? The aspect ratio is no more unity. The aspect ratio will be now less than 1, and as a result of that, the material, the porous material is no more isotropic. There will be different properties along different direction, and typically if the isotropy is only along one direction or in only one plane, you actually end up with a material which is transverse isotropic. Again, more details about this transverse isotropy and orthotropy will be discussed in the future lectures. In terms of the modulus of the composite materials, so again, before I move on to the composite materials, so one more important fact is that although the Young's modulus of cellular materials are very low, as we have seen in the previous slide, but there is a catch. Because of their low density also, the specific stiffness which is defined by the parameter E over rho, that is also low, and there are actually many material indices which you will see afterward, which are actually even like e to the power 0.5 over rho or e to the power 1 by 3 over rho. And because of the low density of the cellular solids, both of these parameters like e to the power 1.5 over rho, so there are cellular solids which are actually even better than the bulk solid, because if you see, you will see afterward that if you just divide the e to the power 0.5 over rho, and if you compare that value with the value for the bulk metal, you will see that the value for the cellular solid is actually higher because of the low density of the cellular solid, and this actually makes cellular solids attractive for many applications where they perform even better than the bulk material. In terms of the Young's modulus of the composite material, alike the cellular solids, they also depend upon several factors. They depend upon the volume fraction of the individual constituents, but also the morphology of the constituents and the orientation of the constituents, they also play a very important role. You will again see these things in much more detail in future lectures, but to give you a brief introduction or brief description, just imagine that you have one fiber reinforced composite. So, as I am showing over here, a fiber reinforced composite, as I have already shown the diagram or the design in the previous lectures, you have, this is a UD fiber reinforced composite. So, have all the fibers along one direction. So, this is one direction and this is two direction. Now, because this is a UD fiber reinforced composite, the composite is designed in such a way that you have the highest property enhancement along the one direction, whereas along the two direction you have less or lesser properties. So, this is a typical case of elastic anisotropy, which depend upon the fiber orientation, with the modulus along the one direction much higher and the modulus along the two direction significantly lower. There are also other aspects, like for example, if we have two different cases of particle reinforced composites, like if you just assume over here in particle reinforced composite, you just assume the particles to be like this in a matrix, and then because the particles do not have any specific orientation or shape, because they are assumed to be kind of spherical or kind of symmetrical and have kind of kind of a random distribution. So, in this case actually you have both along one direction and two direction, you have similar Young's modulus. That means, the particle reinforced composites are typical examples of isotropic materials. However, if you now increase the amount of the particles, that means, if you again in the same case you now increase the particle volume fraction, in that case if your Young's modulus will also increase if the particles have a higher modulus. So, that means, the modulus of the composite materials, they depend upon several factors, in which include the volume fraction of the particles, the morphology of the particle of the reinforcement phase, and the orientation of the reinforcement phase. So, we have seen that in this modulus versus density plot, We also can obtain further or even more information, like as you can see over here, the velocity of the sound in any material is typically given by this equation over here, where V is the sound velocity, E is the Young's modulus and rho is the density. That means, if you now see over here, this equation actually shows us that if now in the plot of Young's modulus over density in double log plot, if we actually now draw contours of straight lines having slope of unity, we actually get the lines of constant volume, because as you can see over here, it is E over rho, and that has been done in the next slide over here. So, as you can see over here in this slide, you can see the straight lines, these dotted lines, and you can see the corresponding sound velocities are also mentioned over there. That means, the sound velocities in any material, they also vary over a wide range, starting from around 10 meter per second to even more than 10,000 meter per second. And all the materials which fall on one particular dotted straight line, they have the same sound velocity. That means, for all materials which fall on the same straight line, sound waves travel with the same velocity or identical velocity through all those materials. Now, I have now here plotted or now shown one straight line, one red line with a constant slope, and you can see that this line actually cuts through the foams, the natural materials like wood, some polymers and also some metals. So, this actually gives us a very important conclusion that all these materials through which the line actually passes, they have the identical sound velocity, and it is a very important conclusion, because that actually allows you to actually enhance your material selection, because all those materials with vastly different structure and morphology will have the same sound velocity. So, more about these plots and how they actually affect the material properties along with the material indices will be discussed in the next lecture. Now, I introduce another plot, which is the strength versus density plot. Again, the plot has a similar appearance. It is a double log plot with strength along y axis and density along x axis. Now, there is one fundamental difference between strength and stiffness. While stiffness is a material parameter and it depends upon the bond strength, strength is not a material parameter and it depends upon many factors. And also, like stiffness or Young's modulus is well defined for all classes of materials, it is not so for strength, and the definition of strength actually varies between different classes of materials. As you will see over here, for metals and polymers, because they undergo plastic deformation, we have the definition of strength as the Young's modulus. So, if you plot the stress strain plot, so this is basically a plot, and somewhere here is the Young's modulus, 0.2% Young's modulus, and this point is taken for metals as the strength in these particular plots. In case of ceramics, it is pretty complicated, because ceramics actually, if you know, ceramics are very weak in tension because of the extremely high brittleness, and ceramics are actually never tested under tensile loading. The compressive strength of ceramics are significantly higher, even to the range of 10 to 20 times higher than tensile strength, but it is actually more common to perform or determine the strength of the ceramics by flexural test. A flexural test is nothing like a bending test. You have a bar like this, and you can have a 3-point bend test, something like that, or you can also have a 4-point bend test, and from that actually you find out the strength of the ceramics. In case of elastomers, it is a tensile tear strength, and for composites typically the tensile failure strength have been used to make this plot. Now, as you can see over here, if you see the data points or the balloons and the bubbles in this plot once again, the metals are at the extreme right hand portion, because metals have the highest density as we already discussed, and ceramics again they have a lower density, but once again many ceramics, if they are technologically very good and they are free from defects, it is very important. Ceramics, to attain a high strength, they should be absolutely free from defects. Any small amount of defect in a ceramic, and if this is under tensile loading condition, it can actually lead to very less amount of strength. Another important point is that in this particular plot, within individual balloons, if you see, the bubbles for the individual materials are pretty long. This is because, as you all know, the strength of materials can be varied over a wide range. Typically for steels, as you know, it depends upon the carbon content, it depends upon the heat treatment, it depends upon whether it is martensite or austenite or bainite, and all those things actually control the strength of the material. Next, what we show over here, this is actually a combination of the previous two plots that we have shown. This is a specific strength over specific modulus. Specific modulus is plotted along y axis and specific strength is plotted along the x axis. So, this is actually again and this plot is very important, because if you want to design a material for lightweight application like automobile application or aerospace application without sacrificing the performance of the material, then it is the specific properties which are most important, and that is why a high value of both specific modulus and specific strength is optimum for the materials designing purposes. And there you see that the composite materials with their most optimum combination of both Young's modulus and strength at a low density is the best material or are the best materials for these applications. Metals, although having good specific having good strength, because of their high density, they actually perform poorer to both ceramics and composite materials. And there are actually many such material property charts. There are several. If you want more information, you should refer to the book by Michael Ashby on material selection in mechanical design. So, next I will briefly introduce in this lecture the concept of the material index. What is a material index? A material index is a grouping of material properties which, if maximized or minimized, a particular material aspect or performance is either maximized or minimized. That means, it can be only one property or it can be several properties in combination. Very often it is a combination of different properties, like as we discussed, the specific stiffness or specific strength, and if these are either maximized or minimized, some function or some performance of the material will be enhanced. So, one case study is being shown over here. This is again taken from the book of Professor Ashby on material selection. So, the problem is that we need to design a material for lightweight beam of square cross section with a given length. The allowable deflection of the beam loaded in bending at its midpoint is constant. So, what are the constraints? The first thing is that the component must function as a beam under bending load, as you have seen from the left hand side image. What are the constraints? The length L is specified, that means the length of the beam is given, and also the load F and allowable deflection delta are also specified, that means the bending stiffness of the beam is also specified. What is the objective of the design? The objective of the design is to minimize the mass of the beam. What are the free variables? The free variables are the cross sectional area, that means the length B, and also the choice of material is also the free variable. The task is to identify the best material which will give the lowest mass without sacrificing the stiffness of the material. Now, from simple beam theory, one obtains the expression for the specific for the stiffness of the beam, which is S, where C1 is a constant, E is the Young's modulus, A is the area, and L is the length of the beam. And also, if we know the mass of the beam, which is nothing but the volume multiplied by the density of the material. So, if you take volume is area over length or area multiplied by length, that means A multiplied by L into rho, that will give you the mass of the beam. And now, if you just replace A from both the equations, you end up with the expression for M, where the terms in the first bracket are already constant, because the stiffness of the beam is already given or kind of mentioned, the length of the beam is also constant, and actually the third part or the part which is in the bracket rho over e to the power half, this is actually called a material index. That means what we have to do, we have to actually optimize this parameter rho over e to the power half to actually minimize the mass of the beam without sacrificing the other properties of the beam under study. And this will be discussed in the next lecture in more detail. So, what are the topics we discussed today? In this lecture, we introduced composites, a class of hybrid materials, and we showed that the composites actually provide the best combination of both specific stiffness and specific strength. And that is why we also showed that the composite materials are ideal for lightweight applications which require both high value of specific stiffness and specific strength. While ceramics have good stiffness, they suffer from their lower strength, while metals, while they have good strength, they suffer from their high density. If we can actually fabricate a good composite material combining the bulk materials like metals, ceramics and polymers, we can actually achieve the combination of specific stiffness and strength not achievable by the individual bulk materials. Then we also introduced the concept of material index and how they can be used to actually maximize or minimize the performance, and we also discussed that a performance of a material or a component is not determined by only one particular property, rather a group of material properties which in combination are called material indices. As a reference, I refer to the book of Mike Ashby and one research paper where the effect of the influence of the pore aspect ratio on the elastic properties of porous materials have been discussed in detail. In the next lecture, we will discuss in more detail about the case study we just introduced, where the material index rho over e to the power half was introduced, and then we will be discussing more about the hybrid materials possibility and the idea of hybridization, and also the concept of one rather new class of composite materials or hybrid materials known as functionally graded materials will be introduced. Thank you very much.